Artificial intelligence has created an energy problem that big tech cannot solve with better software alone. Google, Amazon, Meta, Microsoft, Oracle. They're investing billions of dollars in artificial intelligence and the data centers required to run it. But those data centers need something very physical: electricity, a lot of it. And they need that electricity 24 hours a day. At the same time, many of these companies have made ambitious commitments to reach net zero, so they face an extraordinary challenge. How do you dramatically increase electricity consumption while dramatically reducing emissions? In our previous investigation, we examined how the AI boom is putting big tech's climate commitments under pressure. This time, we're looking for solutions. From renewable energy and batteries to on-site fuel cells, carbon capture, green hydrogen, nuclear, geothermal, and an expanded electricity grid. The question is no longer simply, can big tech reach net zero? It's this: how do you build enough clean, reliable power for the AI revolution? A conventional commercial building can reduce electricity consumption. A hyperscale AI data center is different. Thousands of processors can operate continuously. That requires cooling, power conversion, backup systems, and an electrical infrastructure capable of supporting extremely large loads. Efficiency improvements absolutely matter, but efficiency alone may not solve the problem if computing demand grows even faster. So big tech increasingly faces two energy challenges simultaneously. First, find enough electricity. Second, make that electricity increasingly low carbon. The real solution has to address both. The most obvious starting point is renewable electricity. Solar and wind are scalable. Their operating emissions are extremely low, and large technology companies can support development through long-term electricity purchasing agreements. But there is a problem. The data center needs electricity continuously. Solar output changes throughout the day. Wind output changes with weather conditions. An AI data center doesn't simply shut down every time renewable production falls. So renewables are a major part of the solution. But for a 24-hour load, generation is only the beginning. The next layer is energy storage. When renewable electricity is abundant, batteries can charge. When renewable output falls or electricity demand increases, batteries can discharge. But batteries have another limitation. The amount of energy that must be stored grows with the duration of the shortage. Covering minutes is one problem. Covering extended periods of low renewable generation can become much more demanding. So batteries can play an enormous role. But AI's 24/7 electricity requirement raises a deeper question. What provides firm power when renewable generation and short-duration storage aren't enough? And this is where the solutions become much more interesting. Consider what is happening with Oracle and Bloom Energy. Oracle is developing enormous AI computing infrastructure, and, like other hyperscalers, it needs access to electricity quickly. But connecting very large new loads to the conventional electricity grid can take years in constrained regions. New transmission may be required, new substations may be required, and interconnection studies can take time. Bloom Energy offers a radically different answer. Instead of waiting for all the electricity to arrive through the conventional grid, generate electricity directly at the data center. Bloom's energy server uses solid-oxide fuel cell technology. Rather than generating electricity through conventional combustion, the system electrochemically converts fuel into electricity. The modules can be installed close to where electricity is consumed. That creates something enormously valuable in the AI race: speed to power. Oracle has expanded its relationship with Bloom as it develops AI infrastructure, and Project Jupiter in New Mexico provides an extraordinary example of how this model could work at very large scale. Instead of thinking about the data center and power plant as separate pieces of infrastructure, the two increasingly become one integrated energy campus. But it creates another question: what fuels the fuel cells? Today, Bloom Energy servers can operate using natural gas, and natural gas has an enormous advantage. Infrastructure already exists. Pipelines already cross large parts of the United States. Combine that existing fuel infrastructure with modular on-site fuel cells, and suddenly an AI developer has another pathway to 24/7 electricity. But there's an obvious problem: carbon. Natural gas is still a fossil fuel. So if AI companies simply respond to grid constraints by installing enormous quantities of new natural gas power generation, they may solve the electricity problem while making the net zero problem harder, unless the carbon can be addressed. Fuel cells create an interesting possibility. Bloom's solid-oxide architecture can produce a relatively concentrated carbon dioxide stream compared with conventional combustion exhaust. That could potentially make the CO2 easier to separate. Natural gas enters the fuel cell system. Electricity goes to the AI data center. Instead of releasing all of the resulting carbon dioxide into the atmosphere, the CO2 is captured, compressed, transported, and permanently stored underground. If it works economically and at scale, it could create an intriguing bridge. But we need to be careful. Near zero is not automatically net zero. Carbon capture requires additional equipment. It consumes energy. Capture rates matter, and upstream methane emissions from the natural gas supply chain still matter. Carbon capture could therefore become part of the solution. But Bloom's fuel cells offer another pathway: hydrogen. Now imagine replacing natural gas with hydrogen. Bloom's solid-oxide fuel cell technology can operate using hydrogen. Solar and wind generate power. An electrolyzer uses electricity to split water into hydrogen and oxygen. The hydrogen is stored. Then the hydrogen feeds a fuel cell, and that electricity powers the AI data center. At the point of use, there is no carbon dioxide from hydrogen in the fuel cell. Hydrogen could potentially serve another role as well: backup power. Hydrogen fuel cells could potentially replace some diesel generators without producing carbon dioxide at the point of use. But once again, there is no magic solution. Converting electricity into hydrogen and then back into electricity creates energy losses. Green hydrogen remains expensive in many markets, so the engineering works. The harder question is economics. Can green hydrogen eventually become cheap enough to compete with natural gas, batteries, and other sources of firm electricity? Bloom isn't the only fuel cell company relevant to this discussion. While Bloom's current large-scale data center proposition can begin with natural gas, Plug's PEM fuel cell architecture is fundamentally centered around hydrogen. For data centers, hydrogen fuel cells can potentially provide clean backup and stationary power. But the climate benefit depends on how the hydrogen was produced. So the competition isn't simply Bloom versus Plug. The bigger competition is between different energy architectures. Which combination can deliver reliability, speed, scale, low emissions, and most importantly, acceptable cost? And there is another technology that big tech is increasingly taking seriously: nuclear power. Nuclear plants can produce enormous quantities of electricity. They operate at high capacity factors. They produce very low operational carbon emissions. And unlike solar and wind, their output isn't determined by weather. Existing nuclear plants could provide part of this electricity. Potential reactor restarts could provide more. And advanced reactors or small modular reactors could eventually create new options. But nuclear has almost the opposite problem from on-site fuel cells. Fuel cells can potentially be deployed relatively quickly. New nuclear projects can take years. So nuclear may become extremely important for the long-term AI electricity system. But big tech also needs solutions for data centers being built now. Then there is geothermal. Using modern drilling techniques and improved subsurface engineering, developers hope to access heat in many more locations. Firm electricity. 24 hours a day, very low operational carbon emissions. But advanced geothermal still needs to prove that it can scale economically across a much larger range of locations. So again, another promising piece, not the entire solution. And there is one solution that may ultimately matter more than any individual generation technology: the electricity grid. America and other major economies need more transmission, more substations, more transformers, faster interconnections, more generation, and more storage. A stronger grid allows solar electricity generated in one region to serve demand somewhere else. It creates diversity, and diversity creates resilience. The long-term solution to AI's electricity demand, therefore, cannot simply be build more data centers. It also has to be build the energy system capable of supporting them. So what would a realistic low-carbon AI energy system actually look like? Probably not one technology. Large amounts of solar and wind provide low-cost, clean electricity. Batteries handle short-duration balancing. Nuclear and geothermal provide firm, low-carbon electricity where available. Hydrogen provides potential longer-duration storage, resilience, and backup power. Fuel cells provide modular on-site generation. Carbon capture potentially reduces emissions where natural gas remains necessary during the transition. This isn't a competition where one technology has to eliminate all the others. It is an engineering system, and different regions will require different combinations. A data center in Arizona may have a different optimal energy mix from one in Virginia. The winning solution will be the one that optimizes all of those variables together. If big tech genuinely wants AI growth and net zero to coexist, the strategy needs to move beyond simply purchasing enough renewable electricity on an annual basis to match consumption. The goal should increasingly become building and supporting clean electricity systems capable of serving AI loads when and where the electricity is actually needed. Most importantly, companies need to evaluate life cycle emissions. Moving emissions from the data center to another part of the supply chain doesn't make them disappear. Net zero has to survive the entire system boundary. So can big tech power the AI revolution without abandoning net zero? Technically, yes. There is no fundamental engineering law requiring artificial intelligence to run on high-carbon electricity. But technically possible does not mean easy, or cheap, or fast. The hardest challenge may be deploying all of this infrastructure at approximately the same extraordinary speed at which AI computing capacity is expanding. And that's what makes the Bloom Energy case so important. It demonstrates what happens when the AI industry can no longer wait for the traditional electricity system. Power generation begins moving directly to the data center. The next question is whether that power can progressively move from natural gas to captured carbon, low-carbon hydrogen, and other genuinely clean sources. If it can, the extraordinary electricity demand created by AI could become one of the largest new sources of investment in clean energy infrastructure. But if speed wins and decarbonization comes later, the AI boom could lock in enormous amounts of new fossil energy demand. Both futures are possible. The infrastructure decisions being made today will determine which one we get. Artificial intelligence may be built with algorithms, but the AI economy will be built with infrastructure. Data centers, power plants, solar farms, wind turbines, batteries, electrolyzers, fuel cells, and transmission lines. Big tech doesn't necessarily have to choose between artificial intelligence and net zero, but achieving both will require building the energy system capable of making that commitment real. And the race to build that system has already begun. Hydrogen could become one piece of this emerging AI energy system, but whether it makes sense depends on location, electricity prices, technology choices, infrastructure, and project economics. That's exactly the kind of question H2 Hub is designed to investigate. Explore hydrogen project development, economics, and risk analysis with H2 Hub from ReneEnergy at h2hub.reneenergy.com.